today I want to talk to you about diffusion models, and more specifically about a variation of those models called diffusion implicit models that were introduced by Song and al. So diffusion models, they are kind of a hot topic today, right? Because they allow us to create complex and realistic images. And there are a lot of videos and tutorials about how they work and how to build them. But they also have this big problem, which is the long sampling time, right? This method takes a lot more time than the other usual methods, like for example GANs or autoencoders. And this is a problem that the authors try to tackle here. So diffusion, it's initially a random process, right? You take initial input and you progressively add random elements to it. But the key idea here is to get rid of the random aspect of the process. And we'll see that this leads to first a very much higher sampling speed, but it leads also to other interesting properties, like for example it makes coherent and meaningful interpolations between images, like the one we see here. You see two images and you see that there is meaningful interpolation with a lot of semantic elements kept between two neighbors. So with diffusion models, we are in the domain of generative deep learning. So that means that we observe samples from a distribution, like for example here images, and we want to find a way to model the distribution in order to generate new data. So as we say, the general concept of diffusion is to gradually add noise to the input step by step until so the input will be x0. And we add noise step by step until we are left with pure noise, z, and then we train a neural network to revert back step by step to the original input. So those models, we will call them DDPMs, for Denoising Diffusion Probabilistic Models. They operate on a very simple concept, and that gives them a stable training procedure compared to previous methods that we talked about, like GANs and autoencoders. So this leads first to simpler training, and second, better image quality. But as we said earlier, there is this big sampling time problem, because you need to use a neural network at each step. So to give you an idea of the sampling time, on the same hardware, sampling 50,000 images of size 32 by 32, which is quite small, it takes 1 minute with GAN, but it takes 20 hours with diffusions. So that's more than 1,000 times slower. So that's obviously something that we would like to change. So what we will do is first quickly go over the principle of diffusion and its training objective. And then we talk about the changes that the authors introduced that sped up the sampling process. So in DDPMs, as we said earlier, we progressively add noise to an image and train a network to remove the noise added at every step. So we have our original image here, x0, and we make it pass through a forward diffusion process Q. So the forward process uses a Gaussian distribution that we see here, and its mean and its variance, they depend on the image at the previous step. So here the distribution of xt depends on xt minus 1. So the process, it forms a Markov chain, because each step depends on the precedent step only, and not the previous ones. And you can see that the Gaussian distribution, it also depends on the coefficient named alpha, which is defined at every step t. And these parameters, it controls how much noise we add at each step. So the goal being to end up with pure noise. So one nice property about this process is that the composition of Gaussians, it's still a Gaussian. So you have this nice formula here that says that for any t, the distribution of xt given x0, it's also a Gaussian that depends on the coefficient alpha bar, which is simply a compact product of all the previous alphas. So it's easy to generate the image at any step. You take a step here, for example x2, and you can generate it without having to iterate over the previous steps. You simply have to generate the noise once, and then you have your image. So what we want to do here is to revert this process Q. So during training, we want to learn what we call a generative process, P, which also follows the Gaussian distribution, but in the opposite way. So from the more blurry image to the less blurry image. So this distribution, it also has a mean and a variance that we call mu theta and sigma theta. And these functions, they depend on the previous step and also the time step t. So our goal is to learn those functions. So we need to see exactly what it means in terms of training objective for p to be the opposite of q. So we will zoom on one step. So we want our generative process to be the opposite of our forward process. So the question is, how do we learn the functions mu and theta, mu theta and theta sigma, so that p is the opposite of q? So how do we write it as a learning objective? So what we want to do is to find a way to express the distribution of q, not of xt given xt minus 1, but of xt minus 1 given xt. So we call it the reverse process. And we can do this by using the Bayes theorem. So it turns out that the distribution of xt minus 1 given xt is also a Gaussian. And we can determine its mean and variance that we call the mu tilde t and beta tilde t. So now the two processes that we want to compare, they go to the same direction. So it's more easy to be able to compare them. So here are the formulas for mu tilde t and beta tilde t. So we know that the mean, it also depends not only on xt but also on x0. This is actually a requirement for the distribution to be tractable. But remember that it's fairly easy to make a direct link between xt and x0. So to express xt given x0 and x0 given xt. So we will be able to use that later when we want to further derive equations. You can also see here that beta tilde t depends on beta t in the expression of the variance here, but beta t it's simply equal to 1 minus alpha t. So it's also a parameter that controls the speed of which we add the noise to the image. Right, so we want our two Gaussians here to be similar, our generative process and our reverse process. So what we can do, we can use the KL divergence, which is a measure of distance between two distributions. This KL divergence, we also find it, for example, in the autoencoder formula. So what we can do is set our objective to reduce this KL divergence. So the question is how to express this KL divergence between the reverse process and the generative process. So we see that it's fairly easy for two reasons. First, we know that the two distributions are Gaussians, right? So we know a closed formula for this case. And second, the authors of the DDPM paper, and in fact most of the authors that work on the diffusion problems, and they choose to set the variance sigma theta as a fixed parameter that we call sigma t. So it's no longer a learnable parameter. So in these conditions, minimizing the KL divergence, it's equivalent to minimizing the distance between means. So it's a good thing because we actually know the means. We know mu tilde t. So in fact, we can even simplify this function mu tilde t by expressing x0 as a function of xt and the total added noise until step t. So our function mu tilde t, it becomes fairly simple. We know that our function mu theta needs to converge towards this function. And now what the authors of the DDPM paper propose to do is to do a reparameterization. Instead of predicting this full expression, they predict only the added noise epsilon. So the learning objective becomes even more simpler. And they show that this reparameterization here, it actually leads to better performance and better stability. So finally, once we have trained our model to predict this noise epsilon, we can plug this noise back to the expression of mu theta, and now we have our expression for the mean of the generative process P. So once we have this expression, once we have this generative process, the sampling, it becomes quite straightforward, right? Because we have the mean and the variance of the generative process. So it's just a matter of sampling from Gaussian at each step. So this is it for DDPMs. So this part was a bit long because we actually need to formulate the forward process and the learning objective. But now let's talk about the generalization of DDPMs. So the authors of the implicit model, they came up with a forward process which is a little bit different. So you remember the forward process in the DDPM, the distribution of each step depends only on the previous step. But here they design another process where each step depends on the previous step and also on the original input, as shown on this graph. So for example, you see the image x0 depends on x1 and also on x0. x2 depends on x1 and also on x0. So I'm saying that they define a new process, but actually they define the completely whole family of forward process, because this process is defined by this formula here, which depends of sigma t, which is a sequence of a vector which is defined at every step t. But we can prove that regardless of the vector sigma that we choose, we keep some of the properties of the original process. In particular, the marginals. So you still have this direct link between x0 and xt. But what you no longer have is this Markovian property that we talked about earlier. So you can no longer define xt given xt minus 1 only. Like here, you now have this definition for xt, and this definition involves x0, the original image. So note that you can derive this formula here. You can in fact prove that it is also a Gaussian, but you don't actually use that in this paper. So the question is, why did we define this new specific family? First, you can verify that the original DDPM process is actually part of this family. In fact, if you set the vector sigma to this specific value, you get back to the original DDPM process that we talked about earlier. But if you set sigma equals 0 everywhere, the forward process becomes deterministic, so it's no longer a diffusion. And the reverse process, it also becomes deterministic, so the same noise xt always leads to the same image x0. So if you use this new process as a base to train a model, like we saw for DDPMs, the generative process, it becomes deterministic also. So first, of course, you have to sample noise, which is also always stochastic, but the rest of the procedure is deterministic. So this is basically the definition of implicit model, right? So this is why we call it diffusion models. But this is, you see that it's different from DDPMs, because in DDPMs, the same noise here xt can lead to very much different images due to the stochasticity of the process. All right, so now we have this large family of processes indexed by the vector sigma. So one cool thing that's for each vector sigma, a new objective function needs to be trained in order to generate samples. But one interesting thing about this family is that the training objectives are equivalent for any value of sigma. So we can show that the training objective, it's actually a linear function of the training objective for the original DDPMs. So the optimal function stays the same. The optimal function for the noise stays the same. So that means that a model trained for the original DDPM process, it can be used for any process of the family. So we can use the noise model that we calculated in the DDPM case and plug it into the formula for the reverse process. And now we have a nice new formula for the sampling generation in the general case. Right, so we can do a little recap. So for the original DDPM, we had this formula for the mean of the generative process. But for the generalization, we have this formula here, which is indexed by sigma. But we remember that both of these formulas, they use the same train model because we have the same training objective in both cases. All right, but yeah, let's not forget our main objective, which is to reduce the number of sampling steps. So the authors, they slightly adapted the process in order to work on a subset of the original steps. So imagine that we have a total procedure of 4 steps. So here, the original x0, x1, x2, x3. Let's say that we want to skip x2 to make our process faster. So we can define a process where the distribution of x3 depends of x1 instead of x2, and also depends on the original x0. And we can generalize that to any subset of the original sequence. So let's say that we have a subset indexed by tau 1 to tau s. So we define so for every step of the subset, we define the distribution given the previous step of the subset. So the definition of the original generative process changes once again here. But the authors, they also prove that once again the corresponding training objective is equivalent to the original training objective. So there is no need to train a model for every possible subset of the original sequence. So the authors, they made some tests regarding the sample quality of the shortened process. So there are a few ways to control the quality of a given image sample. First, you can obviously look at it and judge how nice it is by yourself. But there are some less subjective methods for this, in particular the Fréchet inception distance. So the Fréchet inception distance, it was initially introduced in 2017 in order to measure the quality of samples produced by GANs, but you can also use it for any sampling generation method. So this method, it actually measures the distance between the samples and a group of real images. But it measures this distance not in the pixel space, no, but in the embedding space of a visual models. In this case, we use inception net model, which is a CNN. So we have the embeddings of real images here, for example, and we will have the embeddings of our samples that will end up somewhere. And the measure of interest, it's the distance between the two groups of embeddings. So we hope that since those embeddings, they contain high-level values, they can give us an idea of how two images are similar more in a semantic way. So we consider that the smaller the distance, the more our sample tend to look like real image from a human point of view. So this avoids to manually rate each sample, which will be first not really objective and not really efficient. And now we can see the final impact of the number of steps on the quality of the samples. So here the authors train diffusion models on Cypher 10, and they measure the sample quality depending on first the number of steps, which go here from 10 to 1000. 1000, it's remember, it's the original number of steps in the first paper, and also the stochasticity of the model. So here they tie the stochasticity to a parameter called eta. When eta equals 0, it means that sigma equals 0 everywhere. So it's our DDIM process here in blue. And when eta equals 1, here in orange, it's the DDPM model. So first, you can see that the sample quality here is better in DDIMs than in DDPM for the same number of steps. In fact, for a given number of steps, when you lower the stochasticity of the model, the sample quality always gets better. But you can also see that with DDIMs here, we reach the same quality level as DDPMs so when DDPMs we give it 1,000 steps, we can get to the same image quality in only 50 steps. So it's 20 times speed up for the same image quality. The authors, they also produced samples with DDIMs with different number of steps, but while keeping the same original noise. And since the process is deterministic, it's actually easier to measure the impact on the image. So they noted that when we keep the same image noise, the high-level feature of the image stays the same, regardless of the number of steps of the generative process. So here you have the same noise xt, and you have this generative process when you change the number of steps, and it actually leads to the same high-level features. Here is the bird, but you can see that the details are not the same in every picture. So they suppose that when using DDIMs, the original noise acts as a latent representation of the high level feature of the image, and the sampling trajectory it has more an impact on the details of the image. So with DDIMs, it's also possible to perform interpolation between images. So for example, by doing linear interpolation between two images, and then using the results as an input for the generative process. So this is something that was also possible with the DDPMs, as it's also, you also have a latent state that you can make interpolations between. But with DDPMs, this process, it's stochastic, right? So the resulting images, they tend to not share high-level features with the original images. So they tend to either look like a simple pixel interpolation, which is not really meaningful, or to generate completely different images than the two sources when the stochasticity is higher. So, but here, when we do the interpolation, we can see smooth and meaningful transition between the images. You can also observe this here on this grid interpolation. You can see that okay, you have your 4 initial images of churches, because the diffusion model was trained on churches image. And you can see that for every church, its neighbor share some amounts of semantic detail, semantic elements. So yeah, that's it. So first, 2 things to remember about those models. First, the considerable speed up of the sampling time, which has become 20 times faster for the same image, and the possibility to encode the high-level features of the image into a latent space. Right. So if you have any questions regarding the model or the results, please feel free to type in the comments your questions. Thank you very much.